Okay. So in this talk, I will speak about pricing in resource allocation games. And in this talk, I would like to bridge the gap between an economic research question and then going to optimization related questions. And it will turn out that I will use several methods in continuous and discrete optimization to answer some economic questions related to pricing. And let me start with giving you several examples that motivate the model I'm going to present and to which we will return later to interpret some results in these models. So the first model, pricing, think of tolls in a road network. And the model works as follows. We are given a directed graph and we are given commodities that are specified by a starting node and a terminal node. And the idea is to model road traffic by so-called static ST flows. And the idea is that a continuum of agents, let's say the interval 0, 1, wants to travel from S to T. This represents, the graph represents the road network. And in this model, these edges, they represent the streets and they have a load dependent travel time. Meaning if on this arc here, if there are, let's say, 1/2 units of flowing, then the travel time is 1/2. That means every agent or every commuter that uses this edge needs 1/2 units of time. This is the model. And this has been used in the transportation science literature to model rush hour traffic. And the solution concept to solve this model is the wardrobe equilibrium. And that means this is an ST flow distribution of this 1 unit of flow that wants to go from S to T, with a property that every path that is used, and that means it has a positive flow assigned to that path, this must be, in terms of travel times, minimal. This is the notion of a wardrobe equilibrium. And as you see here, this red path, if you assign 1 unit of flow, I mean, if there is only 1 unit from S to T, then this is the unique wardrobe equilibrium solution. Why is that? If here is 1 unit of flow on the first red arc, the time it takes to get to this black node is exactly 1. And then going down takes 0 time, and this takes again 1 unit of time, and you can check any other path has at least the same length. And even if you change that flow decomposition, that is not an equilibrium anymore. I think this is easy to see. Okay, what is known about these equilibrium flows is that they are inefficient in terms of total travel time. So if we count for every agent now the travel time it experiences, so along this red path, the travel time is 1 on the first arc, 0 on the second one, and 1 on the third arc. This is in total 2. So the travel time for every agent here is exactly 2. Yeah. And one idea to improve the total travel time is to assign prices to some edges. And that means you just increase the effective cost of an edge by charging a price, a congestion price. And the hope is to improve the travel time. So if we do this here, suppose we allow for prices, then, I mean, this price is here lambda E for an edge E. We get a new effective travel time. This is this expression here. And the question is, can we now induce better wardrobe equilibria by assigning the right prices? And in this example, if you just kill this middle arc here by assigning a toll of 1, assuming no money and travel time are on the same scale, otherwise we would just rescale. So if we kill this arc here, the middle arc, by assigning a toll, then the flow evenly splits on the upper and lower path, and we have a system optimal traffic flow distribution, and the travel time for every agent goes down to 3.5. This greatly improves the travel time. So going back, an abstract question is now, suppose we look at the space of all ST flows of value 1. One question arises, what kind of flow distributions, edge flow distributions, can you actually enforce by assigning prices? This space, I mean, might have a nice structure. I think this is a very natural and interesting question, and it would also answer the question whether you can always enforce the optimal solution that minimizes travel time, or you might be interested in totally different solutions, maybe green solutions that minimize some energy function, or whatever you can think of. Yeah, this is a natural question, and that question even holds if you have heterogeneous agents, meaning that some part of the population, let's say, value money and travel time differently. That is also a well-known model. The same questions hold here too. And let me define formally a congestion vector here per edge. U is enforceable if and only if there are tolls, so that F is a wardrobe equilibrium for the instance now with tolls, so that for every edge, we indeed realize this given vector of edge flows. This is the notion of enforceability we define here. And the questions I was raising were, which such vectors can you actually enforce? Is the optimal congestion vector enforceable? I mean, minimizing some objective, or can you compute these prices efficiently? And there is an almost complete answer already. And the answer looks roughly as follows. Suppose we are given U, then we write down this linear program. And the idea is to sum up, I mean, this is a path formulation for every commodity. You sum up all the possible paths, is sum, and ask, okay, suppose a fraction of some commodity I takes that path. This is the effective length of the path, assuming that this flow vector U in fact realizes. Yeah, this is an LP in the variable X. And the characterization that was obtained mid of 2000, say, this last paper was only presenting some preliminary results, but the complete answer was 2004, I think. It says the vector U is enforceable if and only if that LP has an optimal solution where this inequality here is tight. That is the full characterization for this question I was just mentioning. Okay. Now, let's keep that in mind. I mean, we set up a nice LP and we talk about optimal solutions of that LP that characterizes whether this U is enforceable or not. And I mean, it shouldn't surprise you. You get for these inequalities Lagrangian multipliers, and they are extremely natural candidates for your prices that you would like to get. This is also what we will see later. And now I turn to a completely different model. It's a cut for now. Now we go to auctions. I think in your graduate school, at least I know that Sven de Vries is working on such problems. Let me just introduce you what this is about. Now we are given items. E is a set of items 1 to M. We have buyers or players 1 to N, and they are equipped with valuation functions. And these are just functions getting as input a subset of items, and the output is, okay, what is my value for receiving this subset of items? This is the setting. Just normalized conditions. The empty set gives you 0 value, and some monotonicity, meaning the more items you get, the happier you are. Yeah, this is just a normal or standard assumption, and that's it, more or less. And the auctioneer wants to determine prices for selling the items so that every buyer is happy. I mean, playing an equilibrium strategy. This is the definition of Walrasian prices. So a price vector and an allocation of items to buyers is a Walrasian equilibrium if every buyer gets a subset of items that maximizes the quasi-linear utility of that buyer. And the utility is my value of the item set minus what I need to pay. And I need to pay per item a price that the auctioneer has determined. So the question here again is, what kind of, under which conditions do these Walrasian equilibria exist? And let me note one difference to the previous model. This model is inherently discrete. So the strategies of agents are a subset of items that they want to buy. So it's not anymore, let's say, a smooth flow polyhedron. It's something discrete here for the moment. Yet there exists a very nice result. End of 90s, that's even a decade before the models I presented the last page. End of 90s, and Diksha, Daniel, Mama, they set up an LP. The LP has basically the same flavor. You sum up not the path anymore, but now you sum up over the subsets of items. You ask, okay, this is the fraction of player I if he wants to get that item, and the value is already given here. This is the value he receives if he gets this subset of items. And here we more or less randomize per player over all these possible sets he may choose. Okay. And the story of this result is, so when can we sell all the items in terms of a Walrasian equilibrium if and only if this LP here admits integral solutions? Yeah, this is the main result here. So what we see here is we again use kind of an LP that we set up, but in this case we are even able to characterize equilibria that came a priori with a discrete flavor, with a discrete setting. I think this is already notable in a certain sense. And how this proof works is basically, okay, you write down the linear program, you can dualize, you get again, for this inequality here, you get, this inequality just says that you can only give away one item of each type, right? You have only one item of a certain type that you can sell. And for this constraint, you get, again, a dual variable, a Lagrange multiplier that you later on use as prices. And it's maybe a bit intricate how to connect this continuous LP with a discrete model at the beginning, but this is more or less what happens here. Okay, now I slightly switch model. This is the third example I would like to show you. This is denoted bilateral trade. It's very similar to the auction setting, yet it has a slightly different flavor. So the input is a directed graph, and now the players are in fact the vertices of that graph. And the vertices, if there is an edge, that means the start vertex can sell some item or can be engaged in a trade with a end vertex B here. So the source is the seller S and the end vertex is the buyer B for some trade that these two parties can realize. And players, so the nodes, they have valuation functions depending with which neighbor they are engaged in a trade. But the key point here is that a node can be a seller if he has an outgoing edge, but he can be at the same time a buyer if an edge points into that node. So this is the key difference to the previous auction setting. Here, a player is a buyer and a seller at the same time. Okay, and the question in this bilateral trade literature is again, can we find prices, lambda, per edge, so per possible trade, so that every node picks a subset of neighbors and decides to get engaged in a bilateral trade. Yeah, and this is the question if this exists or not. And here one key point is also the subset S star. If we select this, it's a subset of edges of trades. If a trade realizes both the seller and the buyer are engaged in that trade and need to be willing to do that. It's not that I can say I sell an item, but the receiver doesn't want it. This is not allowed here, right? This is the setting of bilateral trade. And in this paper from 2015, Hatfield et al., they proved that competitive equilibria exist for so-called a certain class of valuation functions, namely the gross substitute valuations. And the proof was in fact quite intricate, this existence proof. I don't go into details, but the proof was not via LP duality. Yeah. Okay. Let's keep that in mind, this application as well. I mean, it doesn't look so different, and in fact, it can be exactly treated as all these models before. Okay, the fourth example, this is now a different application. It's a price-based congestion control. Maybe some of you have seen these mathematical models that try to explain the behavior of TCP/IP protocols that determine the flow rate if you have a download or some application over the internet. And this model works as follows. The communication graph is again a directed graph, vertex set V, edge set E, and then edges have capacities U. Players are associated again as commodities, end-to-end pairs, start vertex, and the sync vertex TI. And the strategy space is now the flow polytope. I want to send flow from SI to TI. And the usual assumption is that for the value of the SI-TI flow, I get a utility. This is encoded by this function capital UI. And usually, the more I send, the better it is. But the return, the marginal return goes down. So this is usually a concave function. Okay, the whole point is that if you think about TCP protocol, you get end-to-end information, you increase your sending rate, say, but you do not know the capacity of your path. This is not known to you, and you probe basically. And if you send too much, packets get lost, or you get some end-to-end information. If your packets get lost, in TCP, you reduce your rate, otherwise you slightly increase until somehow you learn the underlying capacity of the network. And what makes it complicated is that you are not the only one using the bandwidth in that network. There are thousands or millions of players doing this at the same time. So this is a huge distributed system. And the interpretation of stable points of TCP is that every edge basically settles into a state where a price is communicated, a congestion price, and everybody, the user sends flow, gets utility, and has to pay the price along the chosen route. And this is this lambda transposed xi term that we subtract here. And the goal is, what are these equilibrium congestion prices? Yeah, do they exist, and how do they look like? This was the question that was, late 90s, asked of traffic engineers and also mathematicians, how that looks like. And there was the beautiful characterization of Kelly et al., end of 90s, saying that if you set up this optimization problem, you maximize the total utility, you have here capacity constraints, then the optimal solution of this problem is in fact the equilibrium, and you get, as Lagrangian multipliers of that inequality, you get these congestion prices. Yeah, this is the fourth application I would like to present to you. And the proof here is, again, this is a convex program. It satisfies strong duality. You get, again, Lagrangian multiplier here that you can use to enforce this equilibrium. So one note here is for that model, I think nothing is known if you ask for integral ST flows. So we talk about internet flows, we talk about TCP, and TCP inherently you have data packets. So the whole application is rather discrete. I mean, the fluid flow, it's an approximation, the continuous formulation, but the application itself is rather discrete. So I think it's a very relevant question to ask for integral flows here. But we will see how we can deal with this later. Okay, the last application I would like to mention is that of electricity markets. Here in that model, I learned over the last year is that power generators, they produce some quantity to sell on an electricity market, and one is looking for clearing prices so that you meet a preset demand of electricity, and every generator decides on a quantity that maximizes his own utility. And the utility is what the cost he has. So this is basically a cost plus what he earns at the market. And here again, a question is, do these market clearing prices exist? Under which conditions? And there exist also some works related here to Alexander Martin and his group. If you impose integrality conditions on, let's say, the way you can generate power, then the question of when clearing prices exist, I think is not trivial anymore. And that is somehow related also to this integrality in auctions I was mentioning in the second example. Okay. What I do now is I try to abstract away all these applications. I present you one model. I think in that model, these examples appear as a special case, and then we do some theory on that more general model and try to recover and reinterpret in basically all these results that were known from the literature. So I warn you a bit, it's in the next half an hour, you will not see fancy techniques or new mathematical tools. I think everything I present now is first or second semester mathematics. It's not, I think, not so difficult, but I think it might be interesting for you to see that these models that people have seriously worked on, I mean, if you have the right angle, then maybe it becomes easier and tractable. Okay, the model looks as follows. We have resources, the set capital E, resources 1 to M. We have players 1 to N, and every player has a strategy space. And I assume it's just a subset of R to the M. So far, there's no restriction on this subset Xi. I think this is important to note here. Maybe convex, it may not be. I mean, maybe convex, it may be a polytope, it may be not a polytope, it may be just integer points, it may be an arbitrary convex set. The strategy space is just then a vector in that set, and I use this notation Xij. Yeah, it's the resource consumption of player I on resource J. And the Cartesian product of these sets is the combined strategy space. Yeah, and one element of that is just the strategy distribution, X. This is basically a multi-vector. Each entry is one vector for every player. So the load on a resource J is just, okay, we sum up the strategy of all players and ask, okay, how much do they consume of this resource J? This is it. But keep in mind, Xij may be positive or may also be negative. We allow also for negative consumption of resources. This is not excluded a priori. Okay, this is the model, not more. And now I introduce utility functions of these players. We need to understand how they act, how they behave. And I differentiate between minimization games and maximization games. Okay, let's start with minimization games. And I present these cost functions of a player. I parameterize them in this vector U. U was this capacity vector on the right-hand side. Yeah. And this is now always used as a parameter of our description. And then the cost is just a function that gets the parameter as first argument, but the second argument is the own strategy of the player I. This is an assumption I impose. And in terms of a game theoretic setting, this is an extreme strong assumption that I impose here. This assumption says that the strategy of one player I, in fact, only depends on its own strategy. Yeah, there is an dependence, but this is with respect to a parameter that we input a priori. But otherwise, the cost only depends on the own strategy at this point in time. For maximization games, the same holds true. Okay, but if we go back now to all these examples, in this in the auction setting, my valuation depends on the subset of items I get. This has the property that my utility depends only on the subset of items I choose. Let's take aside the price component, what I need to pay for the moment. In the flow control TCP setting, my utility only depends on the flow I send from SI to TI, keeping aside the price component. And you check this for all these applications I was presenting before. Okay, I define this notion of enforceability. So this vector U that we use to parameterize the game is called enforceable by this tuple x star and price lambda, if and only if U is realized as load, yeah, by this x star, and xi star is in fact an equilibrium for every player. And this is the equilibrium condition, right? Every player minimizes its own effective cost. The same for maximization. And we say weakly enforced with market prices if this complementary slackness holds. That means if a resource is underused, then the multiplier is 0. Yeah, this is the Walrasian setting of market prices. Okay, now we come to the Lagrangian duality. I think that everybody knows. So we define this master problem. So in the objective, I just sum up all players' cost functions. Suppose we stay now in the minimization setting, maximization goes analogously. We impose this capacity restriction of this vector U, and we just ask here for feasibility. This is the master problem. We can define the Lagrangian by just coupling, taking out this constraint and forming the Lagrangian dual. And this is the Lagrangian function with a multiplier lambda. And the dual function is here, we take the infimum over these primal feasible solutions. I think this is standard. Oh, okay, and the dual problem is, as you know, we take the supremum of this dual function over, and the argument are here the multipliers. Okay, and we have, as you see here, non-negativity constraint because we have here a less or equal constraint. This is the analog. Okay, duality gap, we say a problem has 0 duality gap if there is a dual solution and a feasible primal solution so that primal and dual coincide. This is also standard, you know that. And now one key lemma is the following. The Lagrangian function is separable. And this follows, what I mean with this is if you have an argument minimum, an x, this holds true if and only if for every player we have here an argument minimum for the player-specific problem. Yeah. And this is due to two things. I mean, this resource usage, we can decouple it per player. And the objective here, by assumption, that only depends on what player I does. So that's also decomposable. So we can really decompose this Lagrangian. That's just by assumption. That's, I think, a two-liner. This almost requires no proof. Good. So given this, we have this theorem. The capacity vector U is enforceable if and only if this master problem has zero duality gap and admits an optimal solution where this inequality is tight. So let's prove it. The reverse direction, we have just, we have just seen this lemma where we decompose the Lagrangian. We have seen that already. So for the necessity, we can write down the dual, decompose, and then use that this here just vanishes by the property that this inequality is tight. Okay, now we have here a necessary and sufficient conditions. So this is more or less a complete answer to the question when U is enforceable. So let me put this into perspective for a moment. So as I said, in the routing literature, the LP exactly corresponds to that program that I was presenting. And they use strong duality to show these enforcing prices. So that idea is not new. The same for the Kelly framework. He uses, with his concave bandwidth utility functions, we have a convex program. He uses strong duality for his program, and that follows the same vein. For discrete auctions, I think the precise connections yet is not clear at this moment, because as you know, discrete optimization problems, it's not clear at all why they should fulfill strong duality, right? This is in general just not true. I can give you a linear integer program that does not fulfill any notion of strong duality. So I think that point is still unclear. But what is clear, this decoupling of these inequalities, this is related to Danzig-Wolff. Also, Bertzikas and Gallagher used this decoupling of separable problems. I think this is well known. And also the sufficiency of strong duality for enforcing, this is also well known. I'm not reinventing here what has been done several times before. But in these works, usually some convexity is assumed to actually argue that we have strong duality that we can use. In the economics literature, there are several economists dealing with economic equilibrium problems, even several which are more general than the one I'm presenting here. And the idea of convexification was used by Starr. But in these works, usually preference relations are convexified, and then some sort of Kakutani fixed point is employed to argue for existence. It is not that people have really looked at an optimization problem formulation. And I think this is also not always possible, in fact. But this is what we do now. So in the remaining time, I would like to talk more about non-convex models. I think this is much more interesting. So suppose we have a generic model here. How can we actually decide for strong duality? Our meta theorem said we need strong duality. This was a necessary condition, in fact. How can we decide that? And how can we actually interpret this LP kind of stuff for the discrete settings? I think this is not entirely clear at the moment. And what I do now is we use some convexification ideas. So I assume now that this set that was arbitrary in the beginning is not arbitrary anymore, but I assume it's compact. For some models, we can relax this even, but let's say it's compact and the cost function is lower semi-continuous. This is the assumption I make here. And an important role plays the convex hull of sets. The convex hull is just the intersection of all those sets that contain a set xi. that are itself convex. I think this is also clear. But in R to the M, you have this powerful result of Carathéodory that says take any point, then you can represent that point as the convex combination of at most dimension plus one many points in your original set. Yeah, this is important to know. This is Carathéodory, and this allows us to represent this convex hull of Xi as this set here. This is the set spanned by all these convex combinations of at most n plus 1 points. Yeah, and this capital lambda is just, I mean, yeah, it's defined below. You see it. Okay. Given this, now we talk about the payoff functions. They are also, I mean, a priori, I did not impose any assumptions for them. I mean, lower semi-continuous was now the only assumption. They may be non-convex or, yeah. And these functions we will convexify now using convex envelopes. And those envelopes, I think everybody here, I mean, you are in the optimization graduate school. I guess I don't need to introduce these functions. These are the convex functions that act as these lower envelopes for a possibly non-convex function f. Okay. And with this Carathéodory representation, we have a very nice and compact representation of this convex envelope. We can take here the minimum of this objective function to represent the value of the convex envelope for a given point x. And here we ask about all possible representation, and we take the best one in terms of the original function f here. Okay, with this, what I do now is I define a new game, which I call the convexified game. And what happens is we just convexify the strategy spaces and we convexify the cost functions, the pi I, with the convex envelopes. This is this new game I come up with here. And why do I do this? We get the following characterization. The vector u is enforceable for the original game if and only if it is enforceable for this new convexified game. This is the insight here. And to prove this, what basically happens is one can observe that, I mean, the convexified game can be treated as before. We have the exact characterization of enforceability by strong duality. So I think it's very important to look at the dual of that master problem for the convexified version. And if you do that, you see this is the dual function. This looks the same as the original game, but here we have the envelopes. And then if you write down the envelopes, you see that these alpha parameters act linear here on the pi I function, and you can take that out. And due to this, we end up here with a dual of the original problem. I think this is also not surprising. This is also a well-known fact in optimization, but I think it is new in this economic situation. So with this theorem, we connect an a priori non-convex model with a convexified model and have here a complete characterization of enforceability. Let's try to get our hands more into more structured problems. We have seen in the auctions literature these discrete type of strategies, so we will dig deeper into this kind of model. So I consider two special cases. Say the first one is, suppose this Xi, the strategy space, contains just finitely many points. So in the discrete auction setting, this is the case. You have a subset of items. If you look at the incidence vectors, these are just finitely many incidence vectors. The convex hull you see here. And the second application is just the convex hull is finitely generated. This is the assumption here. But Xi might be non-convex, it might even have connected components. It's not, it's arbitrary. But I assume that the function pi I is concave on the convex hull. It can be extended to a convex function, to a concave function. This is the standing assumption here. So any linear function would satisfy that. Okay, what one can do is one can show, in fact, that the convex envelope has a very special form. It's, in fact, the optimal solution of an underlying LP that one can write down using these vertices of the convex hull representation. And with this insight, one can, in fact, show that the master problem can be reformulated as a master LP, in fact, in this convexification variable alpha I. And because of this, we get the following theorem. It says U is enforceable for this type of game if and only if this LP now has an integral optimal solution for which this constraint is tight. Yeah. And in the second case, with this concave extension, we need an optimal LP solution where this optimal solution is, say, primal feasible. So in the first solution, I mean, the feasible points were just the integral points. Therefore, it suffices to say it must be an integral optimal solution. In the second application, I mean, you had these connected components. You might have, in principle, also non-integral solutions. But we require here the optimal solution to be primal feasible. This is the condition here in the second application. Okay. So let me go a bit deeper into further consequences of this application. I think having finite points, even in the flow control problem, if you send packets only, this is a problem where you have finitely many strategy profiles. Yeah. I think this case of finitely many strategies is an extremely realistic and important case. So if we look at the LP, we can look also at the dual problem of that LP. And let's do that for the moment. So we dualize the LP in this form here. I can rewrite the master LP as a maximum. I take the minus out, and then I dualize, and I get this dual LP here. And what I would like to tell you now is, by strong duality for LPs, the dual optimal solution and primal optimal solution coincide. This is strong duality. And let's try to solve the dual LP. And how you can solve an LP is, for instance, by the ellipsoid method. I mean, with solving, I mean in polynomial time. This suppose this is what we want to do. We want to solve in polynomial time the dual LP, and we can do so by the ellipsoid method. And in order to implement the ellipsoid method, one needs an efficient separation procedure that tells us in polynomial time whether a point is feasible or not. And the separation problem here, we want to basically, for the dual, it boils down to determine whether these inequalities are valid for a point or not. Yeah, this is the separation problem. And I can relax this problem if I look at that problem below here. And this is the so-called demand problem. If I can solve that problem here, yeah, for one player, I can also decide on the feasibility of a point here. Yeah, this is not really hard to see here. And this problem here below, it has a very special form. We minimize, from a player's perspective, the cost of a strategy plus what one has to pay. So this is basically a best response computation problem. In terms of, let's go back to let's say, the flow control problem. Given prices, I need to be able to compute the best ST flow for me. This is a convex program. I can do that in polynomial time. In the road traffic problem, given a set of prices, I just need to compute the shortest path in order to verify if what the best response is here. So this, in most cases, is a tractable problem. But what I want to do now is the following. for integral problems, as we have argued, we can define the master problem. And with this meta theorem, we connected the master problem, the integral master problem, with an LP, the convexified problem. This was an LP. And we have the characterization that the former is enforced, U is enforceable for the former if and only if for the latter. Now, suppose we can compute in polynomial time the LP value. Then in case that U is enforceable, we have also the optimal value for the integral problem. And now we do the following trick. The LP formulation we have dualized. This is what you see here. And if we can solve that in polynomial time, we can also solve the LP in polynomial time, and we get the objective value. But then if U is enforceable, we get also the objective value for the original integral problem. I mean, that is a striking, if you think about it, we have an integral problem, a master problem, which is integral. By this dualization step, I mean, always assuming that there is an equilibrium, we can compute this optimal value of this integral problem. And this thought, I mean, this Gedankenexperiment leads to the following insight. If the master problem, I mean, the integral master problem is if we can show that this is NP hard, difficult to an NP hard problem, but the demand problem is polynomial time solvable. We can solve the dual, we can solve there by strong duality the convexified LP, and then we would get also the objective value of the master problem. But if that is NP hard, this is, I mean, unless P equals NP, this is impossible. What I want to tell you here is, with this, I mean, chain of reasoning was a bit, I think it's not so easy. With this chain of reasoning, we can employ NP complexity in order to argue for existence of equilibria of our model we started with. I think this is an interesting handle. Yeah, use NP complexity results in order to argue for non-existence of equilibria in your economic model. And in fact, for the flow control model, let's say if you move from one commodity to two commodities, there's a very nice reduction from two disjoint paths from which you can infer non-existence of equilibria already. So you can infer such complexity theoretic results for these models. Another route beyond NP complexity is now to say, okay, what if my master problem, I mean, the original master problem has some property so that I can say already that there exist integral optimal solutions. I mean, that would be perfect, right? Then we can use strong duality of this convexified model and translate again. I mean, then we know that even integral solutions are optimal for the convexified problem. And then we are done. We satisfy the conditions of the first theorem I presented to you. And what are conditions so that this is true? Well, these are conditions related to total dual integrality of the linear system I write down, or box TDI, or if we use polymetroid environments. I mean, these give us special structures, let's say, for the value function in the auction setting. Even discrete convexity or M convexity are precisely giving you conditions under which the fractional relaxation admits integral solutions. And you can use all these methods and theories to argue about the master problem I presented to you and get, yeah. Okay, so let me summarize. In the first example, I talked about congestion games. I presented to you only this non-atomic formulation, but you can also think about discrete formulations where the players do not form a continuum of agents, but are really discrete entities, and then the model changes a bit. But then one can really use these polyhedral methods like TDI systems, total modularity in order to argue for existence of such equilibria. So polymetroids, I won't dig deeper into details here. So in the market setting, it turns out that for polymetroid valuations, I will also not define what this is, one one gets existence results, and this also I mean, if you look at the gross substitutes conditions that is known in the literature, if you write down the master LP, you see that it fulfills strong duality. And this is exactly the right property you need. Yeah, for the bilateral trade networks, I think the configuration LP that one can define, I think that was not known before. So this is a new consequence, I think. For the congestion control application, I mentioned already that one gets with this NP complexity reasoning also negative results immediately that were not known before. And yeah, to summarize, what I tried here is to develop a general resource allocation model. Then I developed standard tools in terms of Lagrangian duality that should not surprise anybody of you. But what I personally find, I mean, and these models then I convexified also in the normal sense, as you would expect. Yeah, perhaps you. I conclude at this point, and maybe we can discuss a bit further. Thank you.